Is that working? Is the question that we want to know. Doesn't look like it. There we go. Cool. Right, welcome back to this. Yeah, that was me just checking it on YouTube, make sure it works. And yeah, here we go. We'll just crack on. I'm not a streamer once again, so there might be some weird streaming things that I don't know what I'm doing. I've got my phone connected for some rough notes. I've got other things ready to go. I've got a calculator, a CRP5, the Jepson student manual, and on the other tab on my computer I have the CAP 697 document ready to go. I'm not going to mess around. I'm going to try get through this at a reasonable speed. Try not to make as many mistakes as I did last time. I will hide my phone screen, and we are going to be using the Airhead ATPL question bank. I would recommend using it, obviously. That's why I'm using it. And if you want a discount code, link in the description for a wee 10% discount. So this is us for the practice home screen. We're going to use all the question providers. We're going to do 42 questions as is in the real exam. And we're going to use all examining authorities. Let's go for it. I'm just going to shut the door quickly. There we go, that's better. So question 1, let's start off with a bang, shall we? Hopefully. I will check the comments and stuff periodically, but I don't think I'll be too active in watching them because, yeah, too much going on at once. Question 1, refer to Dubrovnik charts 19.1 and 19.2 from the Jepson manual. What is the elevation of the highest obstacle on the chart? But they've given us 2 charts. Funny. Okay, 19.1 is this. This is the ground chart for taxiing and stuff. I doubt this is going to have the highest elevation on it. We can see a spot height there of 594 feet. That seems to be the highest one on the chart, so let's not go for that. Now this one. So we're looking for little points with numbers on them. Anything that's got a direction, like normally there's an arrow or it's boxed to show us the highest one. I think I just spotted it there. 5017. That seems to be quite high, considering all the others are 3117, 3817. 5017, very possible though. Elevation. Any other clues? 5017 feet seems to be making sense to me. 5017. Yes, nice one. Question 2. Just check my phone screen. Apologies if my phone screen is up when it shouldn't be. I'm trying to keep track of it. I've got a little thing that should hopefully tell me when we are showing the phone screen. Okay, so an aircraft flying from Aberdeen to Sumbara. Given the following data, the estimated fuel when passing waypoint Gavel is, we've got ground speed, a fuel flow, and a starting fuel. So what we're going to do is speed, distance, time. We're going to work out the distance between Aberdeen and Gavel, and then we've got speed, we'll find out the time, then go to fuel flow. So let's quickly get the distance from Aberdeen, ADN, which is there, up towards Sumbara, which is up here, and that's the point Gavel there. So we've got 3 nautical miles plus 27, that's 30, plus 77 is 107, plus a distance there of 3. 107, 110 plus 21 is 131. So that's our distance. Get my phone up to display our little calculation. So our calculations so far, V equals D over T. Ooh, Jesus, that's rubbish. Over T. And our distance is 131. Next bit, ground speed 162. 162. So our time is going to be 131 divided by 162. Pop that into a calculator and we get a time of 131 divided by 162 is going to be 0.808 blah blah blah. And we've got a fuel flow 420 kilograms per hour. So if we times that by 420, we'll get a fuel flow of a fuel burn of 339.6 kilograms burnt. We'll take that from 1,295. 1295, take away 339.6, and we get 955.4. 955. Cool. Next question, we use this annex, which is 3301 blah 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 blah. Okay. Brake release mass, initial average temperature, average headwind component. Right, I'm going to write these figures down before we go onto the graph. So we've got 57,500 kilograms. We've got 280. We've got minus 10 degrees ISA deviation. Headwind of 18, and find climb time for en route climb 280.74. Okay, wow, what a graph. So first thing I'm noticing is they've given us one graph to cover ISA minus 6 to ISA minus 15. So that's the ISA deviation bit covered, I believe. Then we've got 57,000 kilograms brake release weight, which looks like it's going to have to be interpolated between the 58 and the 56. And we've got pressure altitude of 280, so 280 is here. And interpolate between these two, and they want to know what time. Come on. Time. So 280 was there. Time is the first number, and we're interpolating between 56 and 58, so I'm looking at maybe 12.5 mittens. Cool. And any corrections? Fuel adjustment for high elevation airports, and effect on time and distance is negligible. So is there 12.5 minutes? There is not. What's the closest one? It's going to be 57.5. Closest one is going to be 13 minutes, isn't it? Yes. Good. Just if you haven't used this question bank already, there's quite a good few little features in here. So this will be similar questions. So there's a similar question on the Bristol Ground School question bank. This is, you can add it to little collections that you make yourself. You can add your own personal private notes. You can mark it as seen in the exam. My favorite feature is the comments. So you can see what other students are doing, bit of community. So yeah, Federico said the same thing as me. He probably got an answer of 12.5, and he said the only answer in the range between 12 and 13 is 13. Yeah, makes sense. And then in the explanation section, it's just showing you what to do. these explanations have been written by proper professionals, so they will go into a lot of detail about what you need to know. Hopefully you can figure out on your own, but yeah, that's what the explanations are for. They're to help you, so use them if you need them. Right, next question then. Ooh, we've got type in an answer in pounds. So we've never had to type in an answer before. That's maybe that's something new for some of the new exams. So let's, given the following information for a commercial air transport operation, calculate the maximum possible extra fuel, including any penalty that can be uplifted. So maximum takeoff mass, maximum landing mass, maximum zero fuel mass, driver mass, blah, 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 blah. Fuel penalty for carrying extra fuel, £470 per 1,000 pounds of extra fuel. Fuel penalty, so you're going to burn an extra £470 per 1,000 pounds of extra fuel. And this is the fuel tank capacity. So we can actually go over as long as we take into account the extra fuel burn, is basically what it's saying there. So first things first, we need to find our allowable takeoff mass. So our allowable takeoff mass is either the maximum zero fuel mass plus the takeoff fuel. It's the regulated takeoff mass, or it's the regulated landing mass plus the trip fuel. So let's just work out these numbers first. Maximum takeoff mass is there for us. 87, let's just do it in order actually, that would make more sense. So maximum zero fuel mass, we have 555 100 plus the takeoff fuel. Do we have that written down? We do 226 195. So our first one is going to be 781,295, and we're looking for the lowest of these three. Our maximum takeoff mass is 87530, and then we've got our maximum landing mass 652,000 plus the landing fuel. So our landing fuel is going to be our takeoff fuel, which is 226,195 minus the trip fuel, which is regulated landing mass plus trip. So regulated landing mass is 652,000 plus the trip fuel, which is there 198,620. So that's going to be 850,620. So that is our limit there, that bottom one. 850,620. That is our limit. Then we break it down into the components. So we've got the big vans travel fast down under in Oz. So we've got our dry operating mass, which is these first two, and we've got the traffic load somewhere. Traffic load's there, and we're working out this point here. So we can work out a total amount of fuel we can take on board. So our dry operating mass is 394,100, and our traffic load is 155,215. So take those two numbers away from the allowable takeoff mass, and we get I'm just doing that quickly, minus 155,215, and we get a fuel load that we can take of 301,305. That's our new thing to work towards. And then we've got the breakdown of fuel: taxi, trip, cafe. So taxi fuel, 1,600. Trip fuel, 198,620. Contingency doesn't give us anything but we will need to have a contingency fuel. Planned takeoff fuel is that. Trip fuel, contingency. Or actually, do we just use the planned takeoff fuel? Because that will include all of the trip fuel, and let's just use that. That makes more sense. So we just use the taxi and the planned takeoff fuel because that'll cover everything. So 226195. 226195 plus the 1600 gives us an answer of 227795. So we're not going to go near our fuel tank capacity. With the extra mass that we're taking. So our limit is here, between these two numbers, because the fuel tank is not limiting us. So 301,305 minus 227795 gives us an extra fuel capacity of 73510. But if we take all that, we're going to burn an extra 470 pounds of fuel per 1,000 pounds of fuel. So we're going to burn an extra 73.51, because that's how many thousands this is, times 470 pounds. So I'm going to take the 73.51 times 470, which equates to 34549.7. So if we take all of the extra fuel that we're allowed, we're going to burn an extra 34,000 tons of fuel. 34,000, yes, that makes sense, doesn't it? But then if we load that on, we're going to burn even more. Interesting. Oh, there's no answers, of course. So to me, wow, that's a tricky question. Because if you take the 73,510 that you have room for, you're going to burn an extra 34,000. Fuel penalty for £470 per 1,000 pounds of extra fuel. That's a lot of extra fuel that you're burning. So can we combine those numbers? Because if we take that, then it will balance out. I'm going to combine the numbers and add 73,510 with 34,549 to get 108,059.7. See how this goes, but I'm not too sure. We'll look at the description, the explanation. 108,059, let's call it 60, and submit the answer. Wow, okay, not too far off. So to determine the appropriate fuel amount, we utilise the first of three methods. We utilise the least of three methods. First, we calculate the allowable zero fuel mass by adding the triangle, Yep. 301, 305, that sounds familiar. The tank capacity is subtracted from the tax fuel, resulting in a fuel penalty of 3.5. Hey? So to determine the appropriate fuel amount, we utilise the least of three methods. First, we calculate the allowable zero fuel mass, or actual zero fuel mass, by adding the dry operating mass and the TL, what's the TL? Traffic load, of course, resulting in 3459. Next, we subtract the actual zero fuel mass from the maximum takeoff mass to obtain this. Then we add the trip fuel and subtract, arriving at this to pass. Tricky one. Oh, that's the explanation. Let's see what comments are saying. What the hell is this question? Yeah. Let's see this. Looks like it's laid out well. Tricky one. Which option is correct as regards checking the availability of the GNSS service for flights that will rely on GNSS information for guidance? The availability of satellites is dependent on ground-based navigation aids. No. Because what's the point in using satellites if you've got to use ground-based navigation aids? Satellites may not be available due to the status of the constellation. I think we had this question last time, something very similar, and I was confused because constellation I associate with stars and things like that, but I suppose the constellation of the satellites in the around the Earth. Satellites may not be available due to terrain and or antenna masking. Hopefully be above all the terrain, and the satellites are directly above us, not behind mountains and things like this. The availability of satellites is dependent on the aircraft's equipment. I think it's the status of the constellation. There might be a few satellites behind the Earth rather than behind the mountains and the terrain. Yes. Ooh, hide my phone. It is hidden. Hold on. I'm remembering every so often. So, need to determine the true airspeed if the airplane's weight is 67,500. 67,500 and is flying at 370 outside air temperature is minus 36. So I've just written those numbers down on my rough notes. So anything about just the TAS, but with true air speed. 67,500, so we're going to have to interpolate between 66 and 68. Yeah, it's going to be closer to 68 though. We are at flight level 370, so it's over here. And we've got N1 Mach, kilograms H engine, indicate airspeed, nautical miles, true airspeed. So true airspeed's the bottom right number. So I'm getting two values here of 469 and 461. And 461. And that's 66,000 and 68,000. And we've got any fuel penalties for temperature. Doesn't say anything. Econ air conditioning, engine anti-ice, total anti-ice on. No corrections visible for working out any corrections or anything. So we're just doing interpolation here. So yeah, at 370 we're going to be basically above the tropopause anyway, so minus 36 seems like it's a bit warm. Normal temperature would be about minus 56, and this is ISA plus 20, so that makes sense. Okay, right, and then we're just doing interpolation. So if I quickly show you what I've written down, that's what I've got written down. And then what we're going to do is find out the difference. So 68 to 66 is 2,000, and 1,500 is going to be 3/4 of the way, if that makes sense. So what I'm saying is there's 2,000 in between these two numbers, and if we add on 1,500 to 66,000, we get this number, and that's 3/4 of the way between the two numbers. So if I go 3/4 of the way between these two numbers, I'll find the same thing. So 1 to 9 is 8, 3/4 of that is 6. So if I take 6 away from this, I'll get the answer, which is going to be 463. Explanation. Yeah, there you go. Oh, actually you can't see that because my phone will be in the way. Just a nice interpolation question. Mark the correct statement. If a decision point procedure is applied for flight planning, so the reduced contingency fuel procedure, a destination alternate is not required. The trip fuel to destination aerodrome is to be calculated via a suitable en route alternate. The fuel calculation is based on a contingency fuel from departure aerodrome to the decision point. And the trip fuel to the destination aerodrome is to be calculated via the decision point. Okay, so decision point procedure is applied for flight planning. So what we do is take 5% from the decision point to destination. Trip fuel to the destination aerodrome is to be calculated via decision point. That sounds sensible. The fuel calculation is based on contingency fuel from departure aerodrome to the decision point. No, because it goes to the alternate for contingency, or the second bit. Trip fuel to the destination aerodrome is to be calculated via the suitable en route alternate. It's not really an en route alternate, it's more of a destination alternate. So I'm going to go for the bottom one. Yes. Got any diagrams? Nah. I love it when there's diagrams because it makes it so much easier to look at and explain. I mean, look at that, that's quite a lot of text, but it will all be correct if you want to read that. Given the information below, calculate the maximum range of a single-engine business aircraft in commercial air transportation, excluding any reserves, so no final reserves. Total tank capacity is this: tank fuel, alternate fuel, contingency fuel, fuel flow, ground speed. Okay, total tank capacity is 300 kilograms. Contingency is 5% of trip. Fuel flow, so we can work out a maximum distance, and then ground speed of 130, the maximum range of a single engine piston aircraft for commercial air transportation. So 300 kilograms, 3 kilograms of that will go, and 12 kilograms will go, then 5, okay, fine. We can work this out. We've got a fuel flow and we can work out the time. So let's get my screen up. Total tank capacity, 300 kilograms, 300 kgs. We're going to need 3 kilograms of that for taxi, and a further 12 for alternate, and contingency will be 5% of trip, so we need to consider that later. But that's what, 15, so it's going to be 285 kilograms we have to play with. Our fuel flow is 35 kilograms per hour. We've got ground speed, so we can work out a maximum distance, which is going to be basically 105%, if you think of it that way, of our total trip that we can do, because we need the 5% knocked off, which will be our contingency. Okay, so our time that we get, 35 kilograms per hour, we've got 285 kilograms on board, gives us a time of 8.14 hours. 35 kilograms per hour, 285, yes. Okay, now we've got a speed, distance, time to do. The speed is 130. The distance is what we're trying to find out, and we've got 8.14 hours. So our distance is going to be 130 times 8.14 gives us a distance of 1058.57. That's including a 5% contingency fuel of the trip fuel. Okay, so that's the distance we can do if we take everything into account. That's burning 285. So how much will that cost us in terms of fuel? Interesting one. So I'm going to go with my original, that's 105%. So if I divide it by 105 and then times by 100, I should get an answer. So I'm going for the distance of being 1008 nautical miles, which is there. That's an interesting question. No. Okay. So you are asked to determine the amount of fuel needed for a specific flight and only use that figure to calculate the aircraft's range. This means excluding additional fuel, reserve fuel, and contingency fuel from the calculation. It is important to properly identify the type of aircraft being used and subtract all necessary reserves. To begin, subtract the taxi fuel and alternate fuel from the maximum fuel amount to find the available fuel for the trip. Yes, that's what we did. Subtracting the required final reserve. It said ignoring all reserves. Excluding any reserves. Which together will make up 105% of the trip fuel. To find the trip fuel alone, divide the total amount by 1.05, multiply the trip fuel by the fuel flow rate to determine the flight time for the trip. With the aircraft's ground speed, this flight time can be used to calculate the aircraft range. The wording of the question may be ambiguous, but it's important to remain calm and not overthink the answer. Yeah, that's not a nice question. Excluding reserves, so include them in calculations. Yeah, that's a shit question. That's really not very good. Anyway, we'll carry on. Don't like that. A ground distance of 250 nautical miles shall be covered with a planned true airspeed of 200 knots, fuel consumption 3 kilograms per nautical air mile. So we've got TAS and nautical air miles, fuel consumption, that's good. A ground distance of 250 nautical miles though, so we'll have to convert the ground distance into an air distance. The original fuel planning was made considering the forecast wind component of plus 25 knots. Before departure, the forecast is revised to a wind component of plus 15 knots. How much fuel is required in addition to the original calculation? So we need to do two calculations, one with plus 25 knots and one with plus 15 knots to figure out the difference between the two. That's what's asking. So we've got first things first. 250 nautical miles. So let's convert the well, we're going to have to do it for both, aren't we? So we need to get an answer for 3 kilograms per nautical air mile. So we just have to convert the ground distance into air distance for both and then work out the 3 kilograms per nautical air mile. So if we do TAS over nautical air miles equals the ground speed over the nautical ground miles. It's all proportional. So a TAS of 200 equals nautical air miles. And the ground speed for the first one is plus 25. So that's going to be 200 knots plus 25, 225 over the nautical ground miles of 250. We'll do some rearranging and find out that the nautical air miles is equal to 250 times 200 over 225. I'm going to quickly calculate that. 250 times 200 divided by 225 is going to be the first one, 222.2. So, and then it's 3 kilograms per nautical mile times 3, 666.6. So for plus 25, it's 667, let's call it. Next one, nautical air miles, TAS over nautical air miles equals ground speed over nautical ground miles. TAS for the second one, still 200 over the nautical air miles, that's what we're trying to figure out. Ground speed is going to be now 215 over the 250. Again, rearranging 200 times 250 divided by 215. I'm getting 232.5 5, 6, blah, blah, blah. Times that by 3. Get an answer of, for plus 15, we're getting 698. 698 minus 667, 31. 30. Yeah, nice. See what they're saying. Problem presents with the distance to be flown along with 2 wind components. Calculate the air distances. Yeah, that's what we did. Nice. Hide this again. Cool. Refer to the annex Amsterdam star from the Jepson, blah, blah, blah. The jet aircraft is cleared for the Mollix 2 Alpha, assuming constant ground speed that is equal to the maximum permissible speed at the initial approach fix. What is the estimated time from Mollix to the clearance limit? Mollix, so we're looking for maximum speed at the IAF. So the IAF here is here, Sugal. Okay. It's giving us some altitude constraints, nothing necessarily in terms of speed, but here we go. Unless otherwise instructed, max 250 knots at the initial approach fix. So we're going for a speed of 250 knots. Write that down. 250 knots. And we're going to calculate the distance from Mollix. What are we assuming? We're assuming constant ground speed that is equal to the maximum personal speed at the initial approach fix. We're assuming maximum 250 knots, which we're going to keep from Mollix to the clearance limit. So from Mollix, it's 70 miles, plus a further 13, that's 2030, plus 7.5 is 37.5. So a quick speed distance time calculation. I've written down the numbers there. So it's going to be 37.5 divided by 250 gives us an answer of 0.15, which converted gives us 9 minutes. Yes, 9 minutes. Is that one of the answers? 9 minutes. Nice. An aircraft is flying at flight level 50 with outsider temperatures ISA plus 10. The QNH given by a meteorological station with an elevation of 11,000 feet AMSL is 990. Calculate the approximate true altitude of the aircraft. Just grabbing a drink of water there. Okay, so flight level 50. Draw the effing picture whenever there's these sort of questions. So, do we have any QNH corrections? We do. So 990 is up here. Right, so let's just draw out. So we're at 5,000 feet according to 1013. That's flight level 50. Fine. QNH correction. We've got a QNH of 990. That's going to be further up. And the difference between 990 and 1013 is 23. 23 times 30 is 690. So we're 690 feet lower when we're on QNH. So, and we're working out the altitude. Altitude's based off of QNH, so we do have to consider this. So we go 5,000 feet minus the 690 gives us an answer of 4310 feet. That is our uncorrected altitude. So altitude is 4310 feet. Then we've got a temperature correction. 4 degrees per 1,000 feet per degree of ISA deviation. So 4 feet, sorry. Yeah, 4 feet per 1,000 feet per ISO deviation. So we're 4.31 thousand feet above the ground, but the reading is given from one that's 1,000 feet above. So we're only 3.31 above the ground. It's 4 feet, and it's, these should really be multiplication symbols, and the outside air temperature is +10. So it's a good correction because it means it's a safer correction because it means we're higher than we actually are, because the pressure levels are all spread out. 4 times 3.31 times 10 is going to be 132.4 feet of temperature error. So we add this onto this, 4310, and I'm getting an answer of 4442.4. 4442. There we go. Okay, so hide my screen. Next one, use VFR ED number 4. So I don't have a good way of displaying this kind of stuff, I'm afraid. So you're just gonna have to maybe pause, get the Jepson route manual out yourself and have a look. I'm just gonna mute me for a second whilst I find this chart. Okay, I've got it eventually. You might hear a bit of rustling. Apologies. So we're going from Blauburen, 48 and East 9. So if I try to find that, we've got 48 there, East 9. What's that one? That's East 11. So we're going to be further over this way. That's East 10. We're just going to I suppose if you're German, you might actually know where all these places are, and it'd make it so much easier. But they love using this chart in flight planning, so if you can get familiar with it, then you'll be at a benefit. So East 9 and 48, well, 48.25, East 9 47. Where are you? This is where it's really slow, I'm afraid. And there's not much to show you because I can't do it. So skip ahead if you can. Unfortunately for anybody watching live as I do this, it's going to be a bit boring. And let's try to find the other one, EDTD and EDMC. Jesus, that took a while. Found them. Right. Find the two places. Which of the following landmarks would be suitable to overlay as a turning point in order to not enter any restricted area? So there's a restricted area sort of halfway along the route that we don't want to enter. So we need to think of a point which might be suitable. So we've got mass, what the hell, they've messed up there. So something iceberg, glider, aerodrome. Or we've got Hayingen. Yeah, that would probably be alright. Abelstadt aerodrome. Abelstadt's kind of off the route, so it might not work. The radio mast south of the town of Ballingen. Radio mast, Ballingen. Where are you, Ballingen? Wow, this is confusing. Abelstadt, yeah, maybe. Radio mast. Tricky. There we go, Billingen. That might be alright. But then it's kind of off the route. So what's the first one? MA quarter N Singen iceberg. Moonsingen iceberg? Which of the following has to be suit overlay to turning point not to enter? I mean, all of them are sort of out of the way. But maybe the best one would be a big radio mast. Very obvious. Tricky one. And very boring to watch. Yeah, using the radio mast will allow you to skip both of them. There you go. Fun one. The only thing I can say with those sort of questions is if you're especially that VFR chart, if you're more familiar with it, the better. I don't know my way around Germany at all, so I've not got the local knowledge that might be beneficial. But if you do, or if you can get some, then that's great. Anyway, prior to an IFR flight, when flying the ICAO flight plan, the time information which should be entered into box 16. Total estimated time is the time elapsed from takeoff until landing, taxi out prior to takeoff until taxiing after landing, takeoff until reaching the initial approach fix of the destination aerodrome, taxiing until the initial approach fix of the destination aerodrome. I think it is takeoff until landing. No, takeoff until reaching the initial approach fix. There you go, just straight up facts. For this question, use this annex. Right. This looks like a long one, doesn't it? So estimated takeoff mass and Paris London twin jet. I'm going to write these numbers down before I go into the graph. So we've got 52,000 kgs. Got airport elevation 387 feet. Flight level 280. Wind is 280 at 40. Minus 10 degrees ISO deviation. Course of 340 degrees. And we're looking for the ground distance and ground distance to the top climb. To top of climb. Okay, so wow, bad graph. 52,000 kilograms is our brake release weight. That is this column here. Pressure altitude is 280. 280 is there. 50,000, 280. Our nautical miles through the air is 53. Nautical air miles, is that right? And fuel adjustments, so at the bottom, sorry, it says fuel adjustments for high elevation airports. We're not thinking about fuel, we're thinking about distance, so that's fine. Effect on time and distance is negligible, so we can discount a few points of information. So we've got our air distance. We need to find out a true airspeed, actually. That would be helpful. So true airspeed 280 at 52 is 353 true airspeed. And we're going to work out the wind component and ISO deviations covered in this section here, so that's fine. Discount that, discount that. That's the information we need. Cool. So we've got a course of 340, which is sort of up like that, and a wind from 280, which is up like this. So the difference between those two is 60 degrees. If we take that's 60 degrees in there, extend that out a bit. This is going at 40 knots. 40 knots. If we take the sine, we get the crosswind, and the cosine would be the headwind. So we take the cosine of 60, times it by 40, and we'll get the head, which on a calculator, cosine 60 is half, isn't it? Yeah, times 40 is 20 knot headwind. It's making our ground speed. Ground speed is, that was 353, wasn't it? 353. 20 knot headwinds making 333. And then we just do that proportional thing. So the TAS 353 over 53 equals 333 over nautical ground miles. Ground distance, yeah, it's asking for that. And then we'll just plug that into a calculator. 333 times 53 divided by 353, and we get an answer of 49.99, so 50. Boom. Done. Okay, reading some charts again. Let's have a look. Refer to Nantes 91, 92, 93. To which risk should you pay special attention? A lighted obstacle in front of runway 03 might be mistaken for the aerodrome beacon. Runway 03 is here. Light obstacle there, and something there. Could be. Oh, it's in French as well. Does it say any specific things? First contact with Nantes, departure, traffic circuit, special considerations, any sort of perform engine run-ups, transit, first low height circuits only for training aircraft and VFR, special VFR minima. Okay, so east traffic circuits should be preferred for noise abatement reasons. East. Grand low areas on the approach to runway 03. It's just quite weird. Increased traffic of gliders and microlights has to be expected. Why would that have to be expected? Runway incursions can occur because a holding point is located at a great distance from the runway. Holding point isn't that long a distance from the runway, so I don't think it's that. Each tickets are available only with air traffic controller clearance. Risk of runway incursion hotspot HS. Where's HS? There. Ah, okay. So they've given us a risk. Risk of incoming in runway. Single holding point located for upstream of the runway. So yeah, that one for runway 21. It doesn't specify runway, does it? Going for that one. Yeah. For these sort of questions, look for specific things that are written on the chart. Don't just do what I did and sort of try and analyze. Look at the chart and it says bottom right HS, HS, runway incursion hotspot. HS stands for hotspot. Next question. Consider a twin engine short haul jet. Okay, 53,000 kilograms, no longer required, holding fuel consumption 4,000. Due to adverse weather, the flight crew needed to use all the fuel initially planned for any contingencies. What quantity of fuel will remain in the tanks after landing? A twin engine short haul jet. Ah, right, okay, so 30 minutes holding. So 30 minutes of holding is 2,000 kilograms of fuel. Due to adverse weather, the flight crew need to use all the fuel initially planned for any contingencies. What quantity of fuel will remain in the tank after landing? So if we've got final reserve intact, it should be 2,000. 3,000. Don't rate that. Using the Alicante 10.3A. Okay, I'll get that out. Bear with. Okay, I have the chart up here, 10.3A. Your departure is Caton 3 Alpha. That one there, okay. And you're clear to flight level 80. Due to a restriction, you have to remain at 2,000 feet until passing the ALT VOR. Okay, so we're at 2,000 feet at ALT. Rate of climb is 800 feet per minute and ground speed is 133 knots. When are you going to reach the top of climb? So we've got 6,000 feet to cover vertically, and we're going 800 feet per minute, and we've got a ground speed of 133 knots. So we can work out time to the top climb with our rate of climb. Oh, I've got to switch to Q the flight level 80 as well. So 10.4A to 10. Okay, so we've got 6,000 feet to cover, but that's up to, that would be 8,000 feet. Okay, right, so if we convert these both, sorry, I'll bring up my screen. If we convert these both into, we're at 2,000 feet until passing. So let's say we're 2,000 feet here. That's based off of 1040. When we change to 1013 to get up to flight level 80, we're going to actually have to climb, what's that? That's 1040 minus 1013, 27. That's 810 feet difference. We're actually going to have to climb up to 8,810 feet. And then when we switch to 1013, we'll wind, wait, sorry, I'm struggling to think here. we need to go up to 8,000 on 1013. If we change that 8,000 to be based off of 1040, then that's going to be 1013 down there. That's 1040. So we need to add on another 810 feet. Yes. So we actually need to go to 8810. Yes. So that's going to be 6,810 feet that we need to cover. That makes sense? Yes. So we can get a speed, distance, time for the vertical. We've got 800, distance 6,810 to give us a time. That's feet per minute, that's feet. So it's going to give us a time in minutes. 6,810 divided by 6,810 divided by 800 gives us a time of 8.5 minutes. And then we're working out a distance that we'll cover in that time. So again, V equals D over T. We've got 133 knots ground speed. We're working out the distance. We've got a time of 8.5 minutes. Careful to check the units. So 133 times 0 hours and 8.5 minutes gives us a distance I'm getting of 18.8 nautical miles. And then we need to figure out how far along that is. So Vilna is 20 miles away. Which is about, well, 19 would be 1 nautical mile before. If we round the distance up to 19, that's going to be 1 nautical mile before Vilna. Yes. Cool. Next question then. For a planned flight, the calculated fuel is listed below. How much fuel should be aboard to cover the rest of the flight if the remaining flight time to destination is 1 hour 45? Trip fuel sufficient for a planned flight time of 4 hours 45. Operator specified reserve fuel 30% of the trip fuel. Right, what is the question? How much fuel should be on board to cover the rest of the flight if the remaining flight time to destination is 1 hour 45? So we're going to have trip fuel is that. Block fuel is 890. Block fuel. Okay, so let's just get our takeoff fuel. Block fuel is 890. And startup and taxi is 35. So we'll take 35 from that and we'll get 855. Yeah. Fuel is sufficient for 4 hours 45, but we don't have a fuel burn. So 855 is equal to 30% plus 4 hours 45. So we could do 4 hours 45. This is weird. 4 hours 45 plus 30% of the planned trip fuel. So if we add 30% of the time, then we could work out how much fuel is on board. 855 is 4 hours 45, and the operator's specified reserve fuel is 30% of the planned trip fuel. So if we extend the trip flight by 30%, then we'll get Yeah, so if I convert this into minutes, that might be easier. So 4 hours is 240 minutes, plus the 45 minutes is 285 minutes. Yes, that is 4 hours 45 in minutes. If we want to add on 30% trip fuel, that's going to be 285 plus 30%. So 285 times 1.3, 370.5 mins. So I'm working out that 855 kilos of fuel gives us 370.5 minutes of flying. Cool. Now what? So we can work out a fuel burn from that. Kilograms per minute, I suppose. Yeah, 855 divided by 370.5 gives us 2.3 kilograms per minute. And then we could work out 1 hour 45 in terms of kilograms per minute. So 105 minutes times 2.3 is 241 kilograms, 0.5 kilograms would be remaining. 241, 242? Nah. That's a weird question. Block fuel 809, take off fuel, yes. Divided by 1.3, not times 1.3, yes, of course. That's where I went wrong. Oh well. Next. Given the following, find the maximum additional load that can be carried. Alright. Allowable takeoff mass again. So we've got maximum zero fuel mass plus takeoff fuel, the regulated takeoff mass, and the regulated landing mass plus trip. Maximum zero fuel mass 53,000 plus takeoff fuel 7,400 equals well, that's 60,400, isn't it? Yeah. Regulated takeoff mass. Wait, have I done the wrong one there? No, maximum zero fuel mass. Maximum allowable 64,400, and landing mass plus the trip fuel is 56,000 plus 56,200, sorry. Trip fuel 4,900 is 61,100. So our most limiting is the first one there, 60,400. And then we've got our dry operating mass, which you can take off that, 35,500. We've got our load, 14,500, to give us a total fuel. Gives us 10,400 kgs of fuel. We need the takeoff fuel of 7,400, so it's going to give us 3,000. Yeah, nice. Cover that up. Wow, I'm getting a lot of mathsy heavy ones. Where's the ones that are just like, here's a fact. A medium jet transport airplane is scheduled to be operated commercially from EGBB to LCPH, Birmingham to Prague. No, Paphos. There is no en route alternate specified for contingency fuel. Based on the following extracts from an operational flight plan, what is the minimum required takeoff fuel? There is no en route alternate specified. Okay, so we're doing no 3% contingency fuel. We've got, is there a decision point? Route distance, air distance, great circle distance, estimated flight time, estimated time to alternate, average wind component, ISO deviation, average fuel flow, holding fuel flow. Wow. Okay. Taxi, trip, cafe. Let's figure out what we've got. Minimum required takeoff fuel. So we can take off the taxi fuel because we don't know what that's going to be. So we need to work out the trip fuel, contingency from that, alternate fuel, and final reserve. We need to do bloody everything. Route distance, air distance. So we need to find the air distance and the average wind component plus. So how long is it going to take to cover the air distance? Like 4 hours and 7 minutes. So the trip fuel, 4 hours and 7 minutes at this 3109. 4 hours and 7 minutes times 3109 kilograms per hour. So I'm getting an answer for that. 4 hours and 07 minutes times 3109. It's going to be 12798, let's call it. Contingency, we're just going to go as 5% of the trip fuel. So let's go for that. 5% of that. 12798 times 3.05 is 640, let's call it. Alternate fuel, we need 23 minutes flying time, and the average fuel flow is here, so 23 minutes of flight time. 0 hours, 23 minutes times 3109 gives 1192, and the final reserve 30 minutes holding above the destination alternate, so it's going to be 2694 divided by 2. It's going to be 1347. So hopefully when we add all that up, final reserve, taxi we don't need because we're going to have takeoff fuel. Trip we've just done. Contingency, there's no specified thing we can do. Alternate, we've got 23 minute flight time. Fuel flow, final reserve, 30 minute holding, destination alternate. There's a lot of picking out the gems of information there, I think. Working out 15977. 15977, 15980. Yes, so yeah, that's just a whole bunch of information. You need to pick out the points that are relevant, which can be tricky when they bombard you with all this stuff. Like why they talk about great circle distance? That's silly. CAT flight is on final approach to the destination airdrome. ATC issued instruction to go around, but no further delays are expected. During the missed approach, it becomes apparent that a new landing cannot be completed with the alternate fuel plus final reserve fuel remaining on landing. What is the best decision for the commander to take? Enter a holding pattern to minimize the fuel flow while deciding whether it's possible to land at destination with sufficient fuel remaining. You've already been told it cannot be completed. Replan a flight without an alternate airdrome, providing a landing can be made with final reserve plus 50 minutes remaining. No. Divert to the alternate to ensure landing can be completed with contingency fuel intact. Contingency fuel wouldn't really be intact. Perform a landing at the destination, providing the landing can be assured and completed with at least final reserve. So this is like committing. You can commit and burn your alternate fuel if the landing can be assured. If there's a second runway, for instance, you wouldn't want to do that lightly, though. That's a pretty big decision. When completing an ATS flight plan, an elapsed time of 1 hour 55 should be entered as 0155. Yeah, nice. Refer to this figure. Planning data shown in the flight log excerpt. After a bulk landing at the destination airport, you have to divert to the alternate airport with the gear extended. The recalculated flight time to the alternate due to the reduced speed is 1 hour 50 minutes. Right, I'm going to write this down. 1 hour 50 minutes. And the fuel flow will be 840 kilograms per hour. Final reserve fuel remains unchanged. What will the estimated landing mass be at the alternate? Okay, so we're going to have an additional. Okay, trip, contingency, ramp, driver mass. Alright, so we've got to say what fuel we would have burnt. Takeoff fuel was 36,040. Yes. And our takeoff mass was this. So we take that off and find out our fuel at destination. Estimated landing mass, or we could just use the estimated landing mass. Does it have that? 74380, but we don't want to use the estimate, we want to use the actual. So takeoff mass 8930. When we get to our destination, we will have burnt our trip fuel. We will have burnt our, maybe not necessarily contingency fuel. Final reserve fuel remains the same. Alternate fuel we're going to burn. Wait, let's work out the mass first. So we don't know if we've burnt any of our extra fuel. We would have just, in theory, burnt our trip fuel by this point. Got our final reserve. So, in theory, when we get there, we will have burnt just our trip fuel from our takeoff mass. So that's what we would burn when we arrive at our destination. That's our estimated landing mass, which is 7430. Yeah, cool. That makes sense. Then we're going to fly for an hour and 50, burning 840 kilograms an hour. And we need to calculate our new landing mass. So 840 kilograms per hour times 1 hour 50 gives us a fuel burn of 1540, which would take off that. We wouldn't have really burnt our alternate fuel. Well, no, we don't have to even consider that. That's fine. 5890 is the answer I'm getting. 5890. Final reserve still intact. Contingency still intact. Extra fuel still in. We're eating into that. That seems to make sense to me. Yeah. Cool. Next ones. Oh god, I feel like I've been going for hours. An aircraft is flying route A to B. Distance is this. Given the following information, what's the distance covered in nautical air miles? So we're going to work out a ground speed and do the proportion thing. Cool. A to B distance is 57 nautical ground miles. So this is our equation we're going to be using eventually. And we've got the following values. So we've got nautical ground miles is 57. True airspeed 125. Given the following information, and we're going to work out the ground speed now and figure out the nautical air miles. Fine. Forecast wind is 240 at 30 knots. 240 at 30. If it's written, it's usually true. Course is 205 magnetic, and the variation is 15. So Cadbury's dairy milk, very tasty. We've got a magnetic here. What do we want to convert? Let's convert the magnetic into true. Variation is 15 degrees west. Magnetic 205. The variation is west, which means we take it off to get the true. So we get a true course of 190. Error check that. If variation is west, magnetic is best. Variation west, magnetic is best. It's the higher number. So our true course is that. 190 going down like this. Wind is coming from 240 at 30 knots. Difference between 190 and 240 is 50. To find out the headwind component, we're going to use the cosine 50 times 30 to give us a headwind component. Cosine 50 times 30, headwind component of 19 knots, making our ground speed is going to be 125 minus the 19, giving us 106. So 125, sorry, I'll just pop that up there. 106. And then we'll pop that into a calculation, make sure we get it the right way around. 125 times 57 will equal, divided by 106, equals the nautical air miles. $67.2. And of course that's none of the answers. 67.2. Maybe they're using the CRP5 or something. So let's say it was a 20 knot headwind that they're using. 125 times 57 divided by 105 gives 67.8. Ugh, still not even close. 240 at 30. 67, close to 66. Of course. Stupid. That's just too close together there. That's silly. Right. About halfway through. More than halfway. Good. Right. Next question. If all other planned and actual data shown in this, ground speed on the leg beta to gamma will be B to G. It's going to be 110 knots. If all other flight parameters remain unchanged, what fuel remaining should be expected at waypoint gamma? Beta to gamma, ground speed is actually 110. So it means our, what's our alpha, beta, gamma, beta to gamma? It's going to be 85 nautical miles. So 110 and our distance is 85. So we can work out we need a time, so let's work that out. So time 85 divided by 110 is going to be, what's that? 46 minutes, I'm getting that as. $85 miles traveling at 110. Yeah, about right. And that's estimating it was going to be 18. I mean, we are going significantly slower, we're going 20 knots slower, yeah, okay. And then we can work out our actual fuel burn and project that forward for the first bit. So we've got a 46-minute leg. And our fuel burn for this first leg, 247 to 2330. 2470 minus 2330 is 140 kilograms. And it took us from 16 to 36, took us 20 minutes. So that's 140 divided by 20, 7 kilograms per minute. 46 times the 7 kilograms per minute is 322 kilograms, which we're going to take off of this to find our fuel remaining. And it's going to be, what's that? 2330, let's just do it in the calculator, minus 322, 2008. 2000, close enough, do we think? Let's go for that. Yeah, nice, bit of rounding errors. Next one, complete line 3 for the sector waypoint B to C was the sector time and the accumulated time to destination. Oh, time and accumulated time. Right, so where are we going from? We should probably write that down. B to C, B to C, B to C. Oh, I've got to do the whole thing. So we've got true airspeed there. I'm going to use the CRP5 for this, I think. It might be a bit easier. So get the calculation done quickly. If I could find a pencil, which I can't, so we'll just wing it. Right, so we're going 125 knots ground speed when we're going this way. The speed increases by 20 knots. So let's work out a new ground speed based off of this. So course is 270. True, and the wind direction is true as well. So 270 is there. We're going this way. Wind is coming from 340, which is up here. Difference between those two is there is 70 degrees off at 20 knots. So cosine 70 times the 20 knots. I'm showing my screen now, and I am not. There we go. Cosine 70 degrees times 20 knots gives us a headwind component. Cosine 70 times 20 gives us a 7 knot headwind. Our true airspeed is what? 135 minus 7 knots is going to be 128 knots ground speed. Okay, and we're using that 128 knots to cover 53, wait no, that's going to be this bit, 53 nautical miles, yes, B to C. So distance, so 128 knots equals the distance of 53 divided by the time. 53 divided by 128 gives us a time of 24.5 minutes, or no, 24 minutes 50 seconds. So if I add 24 minutes sector time onto that, so let's go 24 minutes 50 seconds, and the accumulated time added on to 23 minutes is going to be 47.50. But we can maybe round that up to 25 and 48. 25.48. No? Why not? See, answer image. There is no answer image. What's wrong with that? 25 minutes and the accumulated time 52. Did I get the maths wrong? 23 plus 24 minutes is 40, 25, 49, 48. Right, slow down. 23 minutes sector time. 23 minutes accumulated time so far plus 24 more minutes, or 25 more minutes, let's call it 25, is 48. How is it 52? Cumulative time to destination, that's why. Read the effing question. Accumulated time to destination, not to point C. That's a tricky one. How are we doing? I've got a few wrong. 1, 2, 3, 4, 5, 6, 7 wrong out of 27. Probably just about at 70%. I don't know quick maths on that, but we're doing okay. So finish the endurance / fuel calculations and determine air traffic control endurance for a ATC endurance for a twin jet aeroplane with help of the table provided. More fuel calculations. Trip fuel, that, contingency fuel, we need to figure out. Final reserve fuel this, and we need want times for them all. So we need to work out we've got fuel flow for extra fuel. Okay, so let's just think about this for a second before we go steaming in. We can work out a trip fuel burn, I suppose, at a final reserve time. So trip fuel flow, 5,800 kilograms gets us 2 hours 32 minutes. So that's going to be 5% of the trip fuel we can work out. So that's a nice easy one to start with. 5% is 290 for our contingency. We can work out a fuel burn of 5,800 kilograms divided by 2 hours and 32 minutes. So we're going to be burning 2,290 kilograms per hour. That's fine. So if we add how much that is for the contingency, so 2 hours 32, 5,800, 2,290, and that's going to give us 290 times that. 290 divided by that gives us the 7 minutes of extra fuel. Okay, next bit down is 1,800. I show my, yes, 800, and that gives us 0.42. Final reserve fuel 1,325 at that fuel burn, because they've not given us any more information. Yeah, okay. So 1,325 divided by 2,290 for the fuel burn gives us 34 minutes. Let's call it 35. And then we've got the extra fuel. Are we filling it up to the tanks? Filling it up to the max. We've got no extra fuel. There's no extra fuel on board. But we know what the ramp fuel is, so there must be extra fuel on board. Yes, okay. So let's total this. 5,800 plus 290 plus 1,800 plus 1,325 is 9,215, meaning we've got, and the maximum we're allowed is 9,800 really, because we take off the taxi fuel, minus 9,215. So we've got 585 extra. And at the fuel burn, which they've given us, extra fuel 2,400, so 585 divided by 2,400 gives us 14 minutes, round up to 15, and then we're looking for the total endurance. So we need to add all these up. 2 hours 32 minutes plus 7 minutes, 0 hours 7 minutes plus 0 hours 42 minutes plus 0 hours 35 minutes plus 0 hours 15 minutes. I'm getting 4 hours and 11. 4 hours 12. Oh, 4 hours 7. Oh, it was so close. What's happened? Complete the table. Fuel first, then time. Contingency fuel 5% of trip, 290. Got that. Which is worth 5% trip time, 7.6 minutes, 7 minutes, yes. Minimum takeoff fuel is 9,215. Yeah. Actual takeoff fuel 9,800. Yep. Final reserve for the turbojet. So So what I've done is I have the final reserve here actually could be knocked down by 5 minutes. So we don't need to take, yeah, okay, that's fine. That's fine. Refer to the Amsterdam chart. You're approaching Amsterdam via Rekken to Alpha, which of the following frequencies can be used to receive an ATIS shortly before passing RTIP? Rekken to Alpha. Where are you, Rekken? Rekken to Alpha. Which of the following frequencies can be used to receive ATIS shortly before passing RTIP? Ooh. No. Return to the test. Where are you? There we go. Rekken to Alpha before reaching RTIP. ATIS. 108.4. That's Schiphol. That's the VOR. 132980. Well, that wasn't one of the answers, was it? Short before reaching RTIP. Rekken to Alpha RTIP. 108.4 is the only frequency in the ATIS section. Let's copy that one. Yeah. Oof, more. I'm getting humped with these questions. I don't think you'll have this many in your exam, but who knows. For this question, use Annex 3336. Assume the following distance. Blah, 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 blah. Fuel consumption on such a flight is. Oh, so we've got things to do. Right. Ground distance to be covered, 1,500 nautical miles. Flight level 310. .2 and 470 knots. Headwind plus 40. Planned landing mass is 140,000. ISA plus 15. CFG, and then we've got corrections, fuel consumption. Flight level. Brake release to landing. Reference landing weight 140,000, so that's fine, we've got that. And we've got a nautical air miles, distance, air distance nautical miles, 1,500. So let's come down here. Flight level is 310, which is the first box here. And we've got fuel consumed and time. So fuel consumed is going to be 19693, and the time is 3.21, 3 hours, 21 minutes. That's kgs, yes. Correction on fuel consumption, kilograms per 1,000 kilograms. Correction of what? Okay, let's just check the speeds. We're going correct here. Total anti-ice is on, so we need to add 7%. We've got a pack flow high is plus 1%, and we've we've got temperature, headwind component, true airspeed. Why are they talking about true airspeed? Any kilograms per thousand. What is this correction for? Oh, if we're different from the weight. So we're not different from the weight, that's fine. Plant flow high, so we're adding on 8% to the fuel, it looks like. And alright, so here's another note. ISA plus 15, so we need to do another, so we'll do these first two corrections and then we'll figure out the rest. So let's get into it. So we've got our figure there, 19693 times 1.07 times 1.01. That gives us our correction for the first two bits, which is, I've just rubbed out half the essential information, that's fine. 2128.2 kilograms. That's with the corrections down at the bottom here. Next correction we have is over here. This is our climb profile, descent profile, yes. In the tables, the asterisk means that a step climb of 4,000 must be flown. We've not got any asterisks, but we do have temperature ISA plus 15, and it says that for each degree Celsius above ISA, so we've got 15 of them, apply a fuel correction of 0.01 kilograms. 1 per degree, so that's what we've just done, per nautical mile. Nautical mile, we're doing 1500. It's not going to be very much, but it's nautical air miles. We have a true airspeed, we can work out the nautical air miles, nautical ground speed trick if we want. So it's not that, it's nautical air miles. It's going to be negligible, but we'll do it anyway. Nautical air miles, sorry, TAS equals ground speed over nautical ground miles. TAS is 470. Working out this, ground speed is 40 knot headwind, so it's going to be 430. Nautical ground miles, 1500. So if we do 1500 times 470 divided by 430, got our nautical air miles, which is 163, no, it's 1640, let's call it. So we're timesing this by 1640, 640 times 15 times 0.01 adds a total of 245 kilograms. Okay, fair enough. So add on 240, well, it's 46 kilograms really. 2128.2, and I'm getting an answer of 21528. 21528, 21500. No, where have I gone wrong? I can't even be bothered looking into that. It's just ridiculous. Right, next one. On a flight plan, indicate that you will overfly waypoint Romeo at 120 knots at flight level 085. You will write, what will you write? Romeo, yes. K, no, that's kilometers per hour. N does stand for knots. It's normally F. I think it's going to be flight level first. No, speed first. There you go. Lucky guess. Oh, I'm losing so much enthusiasm for this. This is taking such a long time. Going for 2 hours already. Given the following information for a commercial air transport operation, calculate the maximum possible extra fuel, including any extra fuel penalty that can be uplifted. I don't really want to kind of skip you, come back to you. Yes. Refer to the image. During the flight, the airplane has a failure with the hydraulic system, and the procedure advises the pilots that 2 spoiler panels in each wing are unlikely to save an extension. What would the endurance of the aircraft be? Endurance. Okay, so 4180 is what we've got on board. We've got a final reserve of 1100. And the average fuel flow is 2320. Yeah. Right, keep enthusiasm. Come on, we can do this. Fuel penalty factor, so flaps and slats. 2 spoiler panels. 2 spoilers per wing, 20% increase. Okay, so 2320 times 1.2. We're looking at a new fuel burn of 2784 kilograms per hour. If we've got 4,180 on board, divided by 2784, we're looking at 1.5 hours. Yeah, nice. What does the following text on a NOTAM indicate? Right, so tower services to control arriving and departing aircraft. And issuing clearances, clearance delivery. On the frequency 1210 will be temporary unavailable. Unavailable? Doesn't seem to say that. Friday the 4th and Saturday the 5th of November between 2 and 9. So all this time's the same, 2 and 9, 2 and 9. Right, so tower control arriving and departing aircraft for designated runways. Doesn't say anything about designated runways, that's fine. Tower services to control arriving and departing aircraft will be temporarily available. Services for temporary tower available Friday 4th, Saturday 5th of November between 2 and 1. And frequency, yes, that's on. You're flying a leg of 750 nautical miles with a TAS of this. You calculate that the aircraft burns this. Contrary to the forecast, the wind has changed from this to this, and this is this. How much is the change of fuel used for this leg? Okay. I'm gonna have to work out using the CRP5 TAS of, what am I doing with this TAS on the CRP5 here? I know there's something, sounds familiar. Right, let's just try to work this out. I feel like I'm getting a lot of sums, like a suspicious amount of sums. 750 with a TAS of 350. So let's work out that distance. 350 equals 750 over T. T is going to be 750 divided by 350. That's 2.14 hours. Okay. 35 kilogram per nautical air mile. Contrary to the forecast, the wind has changed from +5 to +10 knots, and the outside temperature is 10 degrees more than planned. Take into account, 0.5% more fuel consumption per 10 degrees warmer air. How much of the change of fuel is used in this leg? So that's 2 hours 14 with a... okay, so I've done this slightly wrong. So if we've got a leg distance of 750 nautical miles, I'm not showing my screen now. 750 nautical miles. Flight level 200, sort of irrelevant. Yes. 350 knots, but we've got a 5 plus 5 knot tailwind. Then we've got a new time, 2.11 hours. 3.5 kilograms, 3.5 kilograms per nautical air mile. So I'm not even working out. I'm just all over the shop. My brain's a bit frazzled. True airspeed of 350. Using the proportion thing again. 350 equals nautical air miles. It was +5 knots, meaning 5 knot tail. It's good for us. And the nautical ground miles is 750. We'll work out the nautical air miles from that. 350 times 750 divided by 355, and we get a nautical air miles of 739 nautical air miles. That is the one for +5 knots. Do exactly the same thing with +10 knots. So we got 350 over nautical air miles equals 360 over 750. 350 times 750 divided by 360 equals the +10 knot one is 729. Let's call it. So that's the initial difference. And we've got 3.5 kilograms per nautical air mile. So consumption 1, consumption 2, 739 times 3.5 kilograms is 2586.5, and the other one is 2551.5. But we're also going to be burning 0.5% more fuel, so times 0.005. 0.01 is 10%. No. I need to do 1 point something. 255 1.5 times 1.005. So the new fuel consumption is 2564.26. So the difference between those two is a difference of minus 22.2 kilograms. Yes, good. What is the distance to the point of equal time? See, this sort of one a little bit easier, hopefully. point of equal time calculation. The point of equal time, the PET, is the total distance times the home speed over the outspeed plus the home speed. Distance from departure to destination, we've got that already, but we're going to work out the ground speeds for both of them. So ground speed for out is going to be, what sort of headwind have we got? True track 320. True track is 320, which is sort of up here. And 160, is that completely opposite the wind is coming from? 160 plus 2 minus 2, yes. So it's coming from 160 at 40 knots. So it's a 40 knot tailwind. So 110 plus the 40 knots, 150 on the way out. And then the ground speed on the way home is going to be 110 minus 40, so it's going to be 70. 70 and 150. The out was 150 plus 70 over 70 times the 340. Do that to the calculator. Divided by 220. I'm getting 108, which is not an answer. Of course it's not. 320 and 160 are opposite on the thing, aren't they? Am I just losing my mind? 320 and 160. I am losing my mind. It's not fully opposite. Right, 320, about there. 160, about there. The difference off the horizontal is going to be reciprocal of 320 minus 2 plus 2 is 140, so it's 20 degrees off. Cosine 20 to find the headwind slash tailwind component times by 40 is going to be a 38 knot tail on the way out. So 110 plus 38 is 148, and 38 knot headwind on the way back is 72, and we've got 340 times 72 up there. Divided by 148 plus 72, and we've got 111. Is that an answer this time? 112. Pretty close. Yes. Okay, next question. Item 9 of the ATS flight plan includes number and type of aircraft. In this case, the number means item 9. Oh, that's if you're doing formation. Number of aircraft flying in a group, number of crash group will be separately using, formation flying. Calculate the following information. Nice. A graph. I've not seen a graph all stream. But I'm going to write down these numbers again so I don't lose them. 3,663 pounds. 74 gallons of fuel. Headwind 40, 8,000 feet cruise, 1,300 RPM, 20 degrees C, lean of peak. Okay, so that's going to be one of the lines, is it? full throttle 23,000. And we've got 20 degrees lean of peak, so we're going to this sort of lines here. We're starting off at a weight of 3663, yep, that's fine. Fuel density, and that's all the good stuff. Takeoff altitude sea level. Yes. So just going in with the numbers, we're going to start off at cruise altitude of 8,000, go all the way across to this line here. The full throttle 2300 RPM one. Follow that along to about there. Yeah, and then we're going down to the bottom to find a distance of just there for 840. That's going to be 840. That's going to be 850, that next big line. So that's going to be 844. I'm getting that as. If that's 850, 2, 4, 6, 8, 10. Yeah, so 842, 844 nautical miles. That's in zero wind conditions. Do we have CHAS? Do we have a ground speed? Do we have anything to do in terms of conversions? We've got headwind. What's the conditions? Mass is this. Aviation gasoline. Wind zero. This is zero wind. This is what makes me think that we've got to do some sort of conversion. We don't have a speed though. So how can we convert this? We don't have if it's in zero wind, that means it's the ground miles. Do I just assign a speed to this? But then no, the higher the speed is, it's not going to work. Am I just supposed to know the cruise speed of this? What is it? See, let's have a look in the graph. See what it says. Nothing. I mean, 844 is the 5 from the graph. With a TAS of approximately 160 knots. Where are you getting the TAS from, sorry? Where the hell is the TAS on that graph? That's just stupid. Stupid. More and more I do this, the more and more I'm getting annoyed with the questions. You're approaching Amsterdam. Reckon to Alpha which of the following procedures should be followed in case of radio communication failure. Reckon to Alpha, this one down here, we saw this earlier. Reckon to Alpha, and I'll say navigation, anything on reckon to Alpha in here. Traffic outside standard arrival route. Radio communication, approaches general, lost communications, cool. Yeah, standard arrival route. Reckon to Bravo. We're reckon to Alpha. Say anything on this? Let's go big. where are we? You're approaching Amsterdam via Reckon 2, so it's got to be this. Arrival, lost communications. Inbound clearance not received. We've got our inbound clearance because we're on the maintain the last cleared and acknowledged flight level. Last cleared and acknowledged flight level. Last level. Cool. After arrival over the fix, intercept the hold. So hold. Commence a descent to flight level 70 at the estimated arrival time last received at EAT. When no EAT has been received and acknowledged, commence descent to flight level 70 at or as near as possible to the estimated time overhead over the holding fix. After reaching flight level 70, leave the holding fix and carry out instrument approach procedure assigned to the runway at flight level 70 approach. Norco 2 Bravo, Reckon 2 Bravo, so that doesn't proceed, that's not us. Right. The appropriate holding fix is RTIP for us. Yes, cool. For procedure provided, continue or direct course. Follow procedures 10.1p pages of your route manual. Doesn't want the specifics. God damn. Which of the following would you expect to find facilitation information regarding customs and health formalities? Not going to be NOTAM'd. It's not going to be air traffic control or charts. It's going to be the AIP. That's the big document with all the info in it. Refer to the flight planner manual. So does this let me draw lines? Oh, that is brilliant. Okay, cool. Somebody said that to me on a comment recently and I completely didn't even know what they were talking about, but right. ISA 15. 6,200 kilograms, 5 hours, 20 mins, and we're looking for trip fuel. Let's work it in. So we don't know the distance. Hey, trip fuel. Alright, so we got a weight. 6,000, 62,000. Trip time. We can work all brake release weights. We've got time. And we can work out ISA plus 15. Okay, so ISA plus 15 is going to be bang in the middle there. Not the most accurate. And then we've got 5 hours and 20 minutes, 5 hours and a half, 5 hours 20. That's going to be straight across. And then five hours 20 straight across and then up to this line. Then we're going to go straight across to the projection line here. All brake release weights. That's where we can find our vertical line for this bit. Yeah, cool. And then we'll go brake release weight of 62,000, which is going to be sort of halfway in between these two. So I'm working the graph backwards. 62, kind of halfway between these two. And we'd go straight across. What's that? 10,000, 14,000 kilograms? Is that going to be an answer? Wow, they're all so close. 13.8. Nah, got to be more accurate than that. That's fine. Right, endurance. Another endurance question. Navigation plan reads trip fuel 100 kilograms. Trip fuel. Is 100 kilograms. Flight time 1 hour 35 mins. Taxi fuel 3 kilograms. Block fuel is 181 kilograms. The ICAO flight plan should read. So we've got block fuel 181, meaning our takeoff fuel is 178 kilograms. We know 100 kilograms of that is trip fuel. Yeah. Well, what are we working out here? We're going to work out a fuel burn. So 100 kilograms is trip fuel, making 78 kilograms left over, and 5% is going to be 5 kilograms, so 73 kilograms is extra unaccounted for fuel. We know that that takes 100 kilograms is 1 hour 35. 100 divided by 1 hour 35 minutes is going to give us 63 kilograms per hour. So our extra fuel on board and our contingency fuel, I suppose. So yeah, 63 kilograms is our fuel burn. Flight times trip fuel, yeah. So 63 kilograms, we know that 5 kilograms of that is going to be contingency fuel. And 78 is the rest. So contingency, 5 kilograms. Well, actually, we could just do 78 kilograms, couldn't we? Yeah. So 78 kilograms, and we get divided by 63 will give us 1 hour and 14 minutes added on to 1 hour 35 minutes, 2 hours 49. Yeah, nice. An aircraft is flying a commercial air transport route and making fuel checks at Tesga and Lamsey, referring to the data from these checks, which amount of fuel could be estimated over Sasal. Tesga, Lamsey. Tesga, actual fuel on board 12.3. Tesga equals 12.3. At Lamsey, we've got 10.7. Overhead Sasal, which is there, so we want to know that. And we could work out a fuel burn in terms of distances. So Tesga, 43, it's 50 more to Osbit, then 64, or we just do times. Well, they've given us the times, so that makes more sense. So you arrived at 47. ATO, actual time overhead. And Lamsey. So that's a time between the two of those points from given the direct at 56 to Osbit, then to KMS. So 47 minutes and then 13. So the time in between those 2 points from 47 plus 3 minutes is, plus 30 minutes, sorry, is on the hour. And then another 30 minutes, that's 26 minutes between those 2 points. So we can work out a fuel burn per minute flown. And we've got we don't have a time overhead, Sasal. We can work it out in distances maybe instead. And maybe it's worth just doing it in distances instead. That's probably the way to do it. So distance between the first 2 points, we've got 40, we've got 50. (43 plus 50, 64. No, 50 miles from Tesco to Osbit. Then 64 to Chemis. Do we have a total distance somewhere? Remaining distance. Okay, so we can compare these numbers. So Tesga 1441 and Lamsey 1220 is 221. Let's check the maths on this. We've got 50 miles plus 64 plus 107, 221. So at Lamsey we'll have 1220, which means at Tesco we've got 221 miles to cover, and we've burnt 12.3 to 10.7, which is 1.6. So per mile we're burning 1,600 kilograms divided by 221. Looks to me like we're burning 7.2 kilograms per mile, knock mile. And then the next distance from Lamsey, remaining distance is these ones to Sasal. 1220 minus 1077 is 143, burning 7.2. So 7.2 times 143 equals 1029.6. So we expect to burn another 1,000 kilograms off this. So let's call it 9.7. 9.6. Yeah. Did I skip question? 31, yeah, that's the one I skipped. Do I really have to do that? Probably do actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't think I'll pass this, you know. You know, I'm just finished with this. 69%. There you go. That was a tricky one. That was very heavy on a lot of things. But there you go. That's I'm kind of just ran out of steam there. I was doing too many with a lot of maths in them. I don't think your exam will have as many as that. You should have a few more graphs in them. 69%, 1% off a pass, and one that I skipped. Let's say that I get that skipped one right, and we push it up to 71%, and job's a good one, you know. I hope you enjoyed that. I certainly didn't. That was tough, and I'll put a vote up shortly for getting the next subject in. We'll figure out the details of what that subject is going to be, and we'll go from there. Probably going to be radio navigation, or I would suspect possibly AGK engines or electrics or something like that. One of the big ones. Get all the big ones out of the way first. And good luck with your studies, good luck with your exams. Hopefully you've learned from some of the mistakes I made, and we'll see you